All right, so that's part B. Now, part C is going to ask us to find the ratio of the rotational kinetic energy to the total kinetic energy the moment it reaches the floor. That's kind of a seemingly weird question, but they want to see what fraction as it hits the floor of the total energy of the object when all of the object's in kinetic energy, and how that compares to what the total energy is. All right, in order to do this, we've got to come up with an expression. Let's get ourselves a new page. So we want to find K rot divided by K tot. Well, what are the expressions? K rot is given by the expression 1/2 I omega squared, which we already said was 1/2 when we plug in I, 1/2 mr squared times omega squared. And we can calculate this number. And what's K total at the floor going to be? Well, K total at the floor is going to be something, right? 1/2 I omega squared at the floor plus 1/2 mv squared at the floor. That sounds like a lot of work. We know that there's no friction in this system. So why not just use conservation of energy again? We know that the K total at the floor by conservation of energy has to equal the gravitational potential at the very top when the object was at rest. So let's just go grab that expression. Since energy has to be conserved from the beginning to the end of this problem, we know that the energy up here, potential energy at the top, has got to equal the total kinetic energy down here when it gets to the bottom, since all of the potential energy at the top is going to be converted by conservation of energy to kinetic energy at the bottom. Let's just grab that expression. That expression is just sitting right here. mg times ht plus the height of the incline. Or rather, this expression, given in terms of things given in the problem. Let's grab it. So u top is going to be mg times h of the table plus length of the incline, sine of theta. So the ratio, k top, or k rot rather, divided by k total is going to be 1/4 mr squared omega squared divided by mg times the height of the table plus d sine theta. Plugging in numbers, m is 0.5 kilograms, r is 0.1 meters, and let's squeeze in our 25.56 radians per second squared, all divided by, again, the mass, which we probably could have just canceled, 9.8 meters per second squared for g, times the height of the table, 0.75 meters, plus d sine theta, which we found earlier to be 0.5 meters. All right, divide these guys out, and this ratio comes out to be about 0.133. No units, since it's a ratio of two things. Boom. So we compared the rotational kinetic energy at the bottom to the total kinetic energy at the bottom, which by conservation of energy equaled the total potential energy, gravitational potential energy that is, at the top. All right, the next step is going to be, they want us to find, after it gets launched, so after rolling off the table, how far horizontally does it go? Well, this is a projectile motion problem from back in chapter 2. We've got to do basically table, ball hits ground, where we know it changed height, h table. Well, we got to look at x motion, y motion, got to figure out what v0 is, all that jazz. So in the x direction, we write down our kinematic equation. And remember, what we always do is we write down the equation exactly as it appears on the formula sheet, and then we check and question mark things that we know and don't know. Boom. Let's look at the x direction first, since that's what we're interested in. We know that in the x direction, we know that we are looking for the horizontal distance x, and they want to call it d. Boom. We can say that we start at the coordinate x naught equals 0. So that guy we know. Its initial velocity in the x direction, that's more interesting. This is really the initial velocity of the center of mass of the cylinder in the x direction. Because in the past, when we talked about velocity, we'd never said it, but we were always really talking about the velocity of the center of mass of the object. We just considered the whole object to be at the center of mass, basically. So we know this. We know v naught x. V naught x is the speed coming off the edge of the table. And that guy is the spinning rate times the radius, because it's rolling without slipping. Roll, no slip. All right, then times time. And we know that the acceleration in the x direction is 0. So we're pretty much good to go there. All right, now in the y direction, we're going to need to use that guy to find the time, because we don't know the value of t. All right. And let's just write here that this is 25.56 radians per second. In the y direction, we know that the final height is 0. The initial height is the height of the table. The initial velocity in the y direction is 0, since it's launched horizontally. Then we have minus 1/2 times acceleration due to gravity, t squared. Solving for t, which we've done many times, this means we have 2 height of the table over g, square rooted. Plug in the numbers, you get about 0.39 seconds. This guy needs to be plugged back in for t up here, and we'll get a result for the horizontal distance traveled d. So d is going to be our omega, our 25.56 radians per second, times our radius, 0.1 meters of the cylinder, times our time it takes to fall, which is 0.39 seconds. All in all, this gets us about 0.998 meters. So a rolling and rotational kinetic energy problem becomes a projectile motion problem. That's a lot of what a lot of these AP questions are after. Compound problems that involve sort of simple cases, even when the system looks complicated, it isn't necessarily going to be that bad. Each step is just going to be using the things that you know and piecing them together in perhaps a unique way. And finally, what they're going to do is they're going to mix different units. They're going to mix a projectile motion question with a torque question, with a rotational motion question, with maybe even an oscillations question, or a momentum one. They like to mix different units, and I think that's useful. The last thing we have to do is compare kinetic energies of the sphere, a sphere and a radius. So what they say is a sphere of the same mass and radius as the cylinder is rolled down the same inclined plane. The rotational inertia of a sphere is about 2/5 mr squared. So we're going to be comparing a cylinder, 1/2 mr squared moment of inertia, and a sphere, which has 2/5 mr squared moment of inertia. And we got to remember that rotational kinetic energy is 1/2 I omega squared, and translational kinetic energy is 1/2 mv squared. We've also got to remember that the bigger the rotational kinetic energy, the smaller the translational kinetic energy, and vice versa. So, is the total kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the total kinetic energy of the cylinder the moment it reaches the floor, part A? Or part I, rather. Well, both guys start at the same height. And both guys end at the same height. They both end at height 0, and they both start at the height of the table plus the height of the incline. Well, if they both start and end at the same height, then they have the same change in potential energy. That means they also have the same change in kinetic energy. So if delta U of the sphere equals delta U of the cylinder, and since they both have the same mass, it does, that means that they both have the same change in total kinetic energy. So, equal to. Number 2, is the rotational kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the rotational kinetic energy of the cylinder? Well, they both start with the same potential energy, but they end with the same total kinetic energy, but this kinetic energy is distributed differently. Remember, because the cylinder at the bottom has a different moment of inertia than the sphere at the bottom, and everywhere that is, his rotational kinetic energy is greater than his rotational kinetic energy. The rotational kinetic of the cylinder is bigger than the rotational kinetic energy of the sphere. Well, that means, and that's because the rotational mass, the moment of inertia of the cylinder, is always greater than the rotational inertia or moment of inertia of the sphere. This means that the cylinder's rotational kinetic energy will be bigger at the bottom. And finally, is the horizontal distance the sphere travels from the table to where it hits the floor greater than, less than, or equal to the horizontal distance the cylinder travels from table to floor? Well, horizontal distance, what was that proportional to? That was proportional to v0, the launch velocity. Well, launch velocity, v0, where does that term appear? That appears in 1/2 mv squared, which comes from translational kinetic energy. Well, just like we said, translational kinetic energy for a set amount of starting potential is bigger for a rotational kinetic energy that's smaller. Whichever one has bigger rotational kinetic energy must then have less translational kinetic energy, meaning less velocity, meaning less launch distance. All right, well, which one had bigger rotational kinetic energy? The cylinder. So since the sphere has less k rot, that means it has more k trans, which means it has more v0, which means it has more horizontal distance traveled d. So finally, we know that the horizontal distance the sphere travels is greater than the horizontal distance the cylinder travels. And I should say we should fix part B. That needs to be the less than check, since they were asking for the sphere as compared to the cylinder. Well, I hope you've enjoyed the solution. Please let me know if there are any mistakes or if you have any questions, and I'll talk to you guys soon.